So this is the continuation of faults, and now we'll be learning the causes of faulting. So first and the most important cause of faulting is overburden stress. Now what is overburden stress? Overburden stress will be any stress which is coming onto the rocks from the top. It can be due to the soil which is present over the top, or if there is any structure which is built over the top, right? So that is considered as an overburden stress. Faults are generally caused by stresses which are acting upon the rocks, correct? Any rock on or below the crust may withstand all the operating stresses up to a limit. So whatever stresses you are putting on the rock will withstand these stresses only up to its limit. But if that stress is increased beyond the limit, it is going to break. And what decides the limit to which it can take strength? It is the cohesive strength and the internal friction of the rock. So how much there is cohesive bond between the material, between the individual molecules and particles, and what is the internal friction. But when that limit is crossed by the operating stresses, the rock yields by fracturing or breaking along certain directions. And for faulting, we need the fracturing of rocks to happen, and only then, if the movement takes place, we get the faulting of the rocks. The displacement may take place essentially along the fracture surface or in different directions and for different distances depending upon the magnitude of the operating stresses, thus giving rise to different types of fault. So depending on the magnitude of what that rock is overloaded with, depending on that, the fracture which is formed, it will move and it will give rise to different types of faults. If we consider three principal stresses, normal faults would form when maximum stress is vertical. So if we have the sigma 1, here we have sigma 2, and in this direction we have sigma 3, then when the sigma 1 is maximum, at that time we will have a normal fault, right? The vertical stress. Second cause of faulting is shrinkage of Earth's crust. Now this is very interesting. The major reason of faulting is formation of fracture and fault planes. Understanding how these fracture planes are formed gives us insight on causes of faulting, right? So to actually the faulting to take place, what we need first, we need the fracture to happen first, right? And how that fracture takes place, if we understand that, then we'll understand the cause of faulting. Shrinkage of Earth's crust is one of the reasons for developing tension in the Earth's crust and causing the rocks to fracture. Now, the shrinkage is speculated by researchers to be formed by following two, and there is still a lot of research going on this, and it has put a lot of questions in front of geologists and other scientists that how the shrinkage of Earth takes place. The first one is that while Earth cools down from a hot molten state, there is a gradual temperature gradient which causes shrinkage of Earth's crust. This can be analogous to shrinkage cracks in concrete due to temperature. So when the magma, it comes on the Earth's crust, and when it cools down here like this, what happens that this portion is exposed to atmosphere and the bottom portion is still hot. So because this is exposed to atmosphere, the top part cools faster than the bottom part. This creates a temperature gradient between the top surface and the bottom surface, and therefore the cracks start happening. This same happens in the concrete as well, because while concrete is being placed, because of that internal reaction of the concrete, there is a lot of heat generated inside, and since the outer atmosphere is a little bit cooler, that temperature gradient takes place, and because of this, some cracks are formed in the concrete. So it is analogous somewhere to that point. Second point is the core of the Earth consists of molten magma. This magma often travels towards the surface due to the convection currents. This is similar to how hot water boiling at the bottom of a bowl travels upwards. This traveling magma causes tangential stresses in the Earth's crust, which causes tension and compression in the Earth's crust, thus causing faulting and folding. So at the core of the Earth, there is a lot of hot molten magma. This magma often travels towards the surface because of the convection currents, and this is same as what happens in a bowl of boiling water. So when you try to boil water by supplying the heat here, you can see the bubbles often traveling like this, which are formed at the bottom. They often travel and they come again down, okay, like this. So this happens due to convection current which is there, because the bottom part is heating and the top part is relatively exposed to the atmosphere, and because of that it is relatively cool, and because of that there is a convection current that is set up inside. The same, using the same principle, this hot molten magma, it goes up like this and then it moves this way. So the movement of this magma like this causes it tries to take the earth's crust with it, so it causes tangential stresses in the earth's crust. These tangential stresses are going to first of all cause tension at this point, because this point is getting separated from this here, so it causes tangential stresses, and here the earth's crust is getting compressed, so it also causes compression and it also causes tension. Due to tension there is a fracture in the rock, and due to compression it can cause folding of the rocks, right? Because there is a lateral thrust which is coming, and we saw in the previous few lectures that how folds are formed because of the lateral thrusts. So this is one of the reason of shrinkage of Earth's crust. The third reason is faulting, which is associated with folding. So the thrust associated with folding often develops when a fracture is formed parallel to the axial plane of a fold, where the shearing strength of the bed is overcome by the shearing stresses responsible for the development of the fold. So if this was a fold, an entirely overturned or a recumbent type of fold, and this is the axial plane, this tries to move like this, it tries to rotate it, and there are a lot of stresses which come on the axial plane, and if the rocks are not able to take those stresses, if the stresses due to overturning they exceed the inherent strength of the rock, then what will happen? It will cause fracture along that plane, and this is going to create your fault. Next we'll understand the engineering considerations of fault. So in aspect of future projects, faults are important for a civil engineer in that these mark the sites where dislocation of ground has occurred in the past and where such dislocations cannot be entirely ruled out in future. So if you are trying to build a certain project onto a certain site, then you should ensure that no faulting had taken place there, and if faulting had taken place, is there a possibility of future fault to be happening at that same place at all? Because if that happens, then it will be a very dangerous thing for the project, right? It is the dislocation aspect which may introduce considerable complications in the site for proposed engineering project. This may necessitate thorough investigations for the stability of the intended project. So what are the problems that happen because of faults, and what are their inferences? What can we make out from those problems? So the engineer has to consider faults and faulting from three angles. First angle is that the effect of faulting on the rocks of proposed project and its suitability to lay down foundation and construct a structure. So if a fault has taken place in a particular region, the engineer has to first check that what is the effect of that fault on the surrounding rocks, whether those rocks have lost their strength, and can a strong foundation be built on those rocks. He has to check that first. Second, to check if faulting has not made the site useless, and if treatment of site is required, and is it feasible, and after treatment will the structure be safe in future from a possible faulting again. So what he has to check second is if the faulting has taken place in that region, and if there is a compulsion that we have to build on that site, so can the treatment of that site make that site strong again? And even after making that site strong, Is there a possibility of future faulting to take place again? That also he has to ensure. Third is, what factor of safety is essential to be adopted in the design and construction of the proposed structure if the site is faulted and there is no alternative available to it. So he has to also see this, that if we have to build anyhow on that place only, then how much factor of safety he has to consider. And mind you that you cannot consider a lot of factor of safety, because that would hamper your budget, because the projects are sanctioned according to the budget. And it should also not happen that it takes a very long time to build a certain project. There is a lot of demand recently, and it puts a lot of pressure on the civil engineer to build the structures economically as well as safe in strength. The answers to the above questions is, the influence of faults on the rock cause very much shearing and crushing of the rocks located along or near the fault surfaces and zones. So this is the answer to the first thing, that what effect of faulting will be there on the rocks. So we have seen that the faults cause shearing and crushing of the rocks, and almost it makes the rock to lose its strength. So it is not suitable to build structures in such places. The faulted rocks will form weak foundations and abutments for dam, even if they were previously strong and impervious. So even if the rock before faulting it was very strong and impervious, after faulting there will be cracks in such rocks. And impervious meaning that it did not allow the passage of water. But if you are building a dam, that is the most important criteria, that the rock should not allow passage of water from the dam from one side to the other side. Otherwise it will basically be the failure of the dam, right? So the faulted rocks will form weak foundation and abutments for dam. The shear and fault zones will serve as easy pathway for water and cause leakage when left untreated in dams and reservoir sites. Once the fault zones, shear zones or fault surfaces become lubricated with water, they become potential areas for further slips and slides. So once faults takes place, and when the fractures happen in the rocks, when the cracks take place in the rocks, if those cracks are lubricated with water, that is if water seeps into them, then it further facilitates easy movement of the rocks against that fracture. Faulting product like gauge and breccia create additional problems. The site has to be cleared of them or taken below to the sound bedrock. What are the solutions for the previous problems? First, the civil engineer has to ascertain for the presence of faults, their type and extent, and also has obtained thorough report from an engineering geologist of the effects caused by these faults on the rock of the project area. So he has to first ascertain that the faulting has taken place in that area and what effect it has caused. The number, size and inclination of shear zones should be given top consideration. So how many shear zones are formed because of faulting? Shear zones would be very dangerous, because if there is a shear zone here, then what it will happen is, because of this rock will move like this past to this rock. So this is what happens in the shear zone. If this is very steep, that is the inclination, if this is steep, the shear zone is steep, then it is easier for this rock to move. But if the shear zone is very like this, if it is not steep, then it is difficult for the top rock to move against it. Ideally, the proposed site for any major civil engineering project should be located as far away as possible from an active fault and never on active faults, first of all. So it should not be built on active fault, firstly, and second, it should be avoided to even be being built in the region near to the active faults. In many cases, faulting leaves the rock only partially affected, and there may not be much choice available for shifting the site of the project. So it happens in certain government projects that you cannot shift the site. The site is fixed. So even if there is a faulting that has taken place, you have to, as an engineer, make that site suitable for the project. And this happened in the Bhakra Dam, the Bhakra Nangal Dam of Punjab. In India, showed occurrence of numerous shear zones in them. So what was the treatment that took place? It was decided to treat the shear zones by extensive excavation of the sheared material and backfilling with cement grouting. So whatever the sheared material was there, that was removed and it was filled with cement. This is called as grouting. So if there is a rock here like this and there is a lot of shearing that has taken place, so what will be done? We will remove this much part. Okay, this much part will be removed and it will be filled with the cement grout like this. Okay, so that will again ensure the stability of that part. The embankments have withstood the test of the time. So this is it for faults, and in the next lecture we'll be learning about jointing. So till then, take care. Thank you.